Welcome to a new unit on thermochemistry. No better place to start than looking at different ways of calculating the energy change that results from a chemical reaction. There are two ways that we can calculate energy changes, and one of them we've kind of mentioned already in a previous unit, and then here's one new option. It's using something called standard enthalpy of formation. Now, this word enthalpy is going to be a big deal throughout the thermochemistry unit. It's a weird word, it doesn't roll off the tongue well, but enthalpy is just a fancy word for heat energy. So if we see a question that asks us about an enthalpy change, we're just wondering about the energy change. Or sometimes we'll look at a transfer of enthalpy. It just means like a transfer of heat energy. By definition, standard enthalpy of formation is the change in heat energy that accompanies the formation of 1 mole of a compound from its elements in their standard state. So that would just mean like their standard state of matter, where something like oxygen is a gas and copper is a metal. These are all constants. You look them up on a chart, or they're constants that would just be given to us when we need them. The symbol that we're looking for is this guy. Delta H is like our change in heat. The little degree symbol means standard state. So the degree here doesn't really mean like temperature. That little degree symbol means that the elements were in their standard state of matter, and then the F stands for formation. So it's the energy change that accompanies the formation of 1 mole of a compound from its elements. Cool. Now there is one thing that we should mention, and that here we said that this heat of formation is for the formation of 1 mole of a compound from its elements. Well, that means that this enthalpy of formation value for a pure element in its standard state of matter is 0. So the elements in their standard state, copper being a metal, oxygen being a gas, they're formed naturally on the face of this earth. And so there's no energy change when I use oxygen gas. That's a naturally occurring element. Now, if I react oxygen with copper to form a compound, now there's going to be an energy change. A chemical reaction is always accompanied by some kind of an energy change, whether it's endothermic or exothermic. And so if you're ever looking at a chemical reaction that involves pure elements, their heat of formation is 0 because they occur in nature. Eventually, then, when I see a chemical reaction and I want to calculate the energy change, we can use this equation. It's totally given to you in the packet. It's plug and chug, so easy to use. Delta H, Rxn, means the energy change for a chemical reaction can be calculated as the sum of the heat of formations for all of my products minus the sum of the heat of formation for all of my reactants. So it's products minus reactants. That seems familiar. This thermal stuff is great. I mean, we'll look at it a little more in depth now, but we've sprinkled thermochemistry through previous units. So there will be things that come up here where you'll be like, oh, I kind of remember that. When we were looking at some graphs. Remember these guys in the kinetics unit? When we had like a endothermic or exothermic reaction, and we wanted to know the energy change. We said, oh, it's like the energy level of your products minus the energy level of your reactants. And that gives you the overall net change for the chemical reaction. Kind of the same thing here. It's just a little different way of calculating the energy change. For a chemical reaction, we're given different data. It's going to look like this. So I've got my chemical reaction, and I've got some heat of formation values. Now, I do see that there are 4 components to the chemical reaction, but I only have 2 heat of formation values. But that's just because aluminum solid and iron solid are elements in their elemental state of matter. So their heat of formation values are 0. So often they don't give me heat of formation for a pure element in its elemental state of matter. And so here's what this looks like. I'm going to start with delta H equals, and then I like to kind of go with brackets. And I want the total energy of my products minus the total energy of my reactants. All right, I can do this. So on my product side, I see aluminum oxide. Now in the balanced equation, there's 1 mole of aluminum oxide, which we do have to look at the coefficients in the balanced equation because these values are kilojoules per 1 mole. If I would have had more than 1 mole in my balanced equation, I would have needed to multiply. But I'm good here. I've got 1 mole of aluminum oxide, and so I'm going to set that up kind of like 1 mole of the Al2O3. I'll kind of set this up, and then I'll plug in all my numbers. And then I'm going to have 2 moles of the iron. Here's what I'm thinking. There's the total energy of my products minus the total energy of my reactants. So I'm going to have 2 moles of aluminum and then 1 mole of iron oxide, O3. Here's what my setup looks like. Total energy of the products minus total energy of the reactants. Now I can just sub the numbers in. So if I plug the numbers in, I'm going to have 1 times the aluminum oxide, which is negative 1,676.0 kilojoules, plus 2 times nothing. 2 times 0. It's an element that is occurring naturally. Products minus reactants. On the product side, kind of similar. 2 times the aluminum, but it's a naturally occurring element, so there is no energy change when I'm working with aluminum solid. Oopsies, I'll put that in a 0 right away. There we go, 0.0. Plus 1 mole of the iron oxide, negative 826.0. And there you have it. Now I just plug it in my calculator, products minus reactants. Total energy of the products minus total energy of the reactants. I plug this in, and I'm getting a delta H of like negative 850 kilojoules. It's that easy. Now, one thing that we should make note of is that once I get my final energy value, and we've seen this, again, like sprinkled throughout other units, that when I have a negative delta H, that means the reaction is exothermic. That this is 850 kilojoules released to the surroundings. I should see evidence of energy being released, whether it's in the form of heat or light. Awesome. So let's try the second one then. Now this one's a little more complex reaction. I'll give you the balanced equation here. If I can scooch it in somewhere. Okay, so the balanced equation would look like this. We've got ammonium chloride, 2NH4Cl, plus barium hydroxide, When they react together, you'll get a solution of barium chloride. And then the other 2 products will be ammonia, which is like that stinky gas, kind of smells like a cleaning product, and water. Here's my balanced equation. Now I do need the balanced equation because I obviously want to know what's a reactant, what's a product, And maybe most important, I need to know the ratios. Because again, these numbers are given as kilojoules per mole, but I do see some coefficients in my balanced equation, which means that I'm going to have more than 1 mole. All right, do you think we can get right after this one? Do you think we can plug numbers in right away? Let's try it. Okay, so delta H is a total energy of all 3 of my products. So I've got the barium chloride, just 1 mole. So that'll be the negative 860 plus 2 moles of the ammonia, negative 46.1, plus 2 moles of water, negative 286.0. And again, these numbers would be given to us. These are all constants. Here's the total energy of all my products, because technically that coefficient is moles, and then these numbers are kilojoules per mole. So I'm multiplying by any coefficients in the balanced equation. Total energy of my products minus total energy of my reactants. All right, so let's see here. 2 moles of the ammonium chloride, negative 314.4, plus 1 mole of barium hydroxide, negative 998.2. Now, I really think that the key to these is staying organized. Obviously, the calculation itself is not difficult, but you just have to keep things organized, and especially now when you start simplifying this and getting ready to plug it in your calculator, we just have to be careful with all these negative signs, especially, I'm going to have like minus a negative value. So sometimes at this point, I like to just simplify the products and the reactants. So if I plug all this in my calculator, on the product side, I'm getting this to be about negative 1,524.2 minus, let's simplify this side too. So if I plug this in, it is negative 1,627. Okay, so now again, I just have to be careful. When I put this in my calculator, I've got minus, a negative. So just be careful. That's usually some of the bonehead reasons why we don't end up with the right answer in the end. All right, so I'm seeing delta H equals, this is going to be positive, isn't it? Yes, it is. 102.8. And then we would use the unit kilojoules. There we go. And so this one had a positive delta H. That positive delta H is telling me that it's endothermic. Positive delta H is endothermic. And so we've used the terms endothermic, exothermic before. In a previous science class, I'm sure you talked about these terms. And now we just have to kind of understand what it means. If something is exothermic, it's releasing energy. It's releasing energy to the surroundings. It could be the surrounding air. It could be the container that's holding the reaction. I mean, maybe the container is going to feel hot. If I have an exothermic reaction happening inside a beaker, it should feel hot to the touch because energy is being released to the surroundings. With an endothermic change, energy is absorbed. I always think like energy in, endothermic. When energy is absorbed into a system, the surroundings are going to feel cool. And so like one way to think about it is to say, if I have a beaker, here's my beaker, and there's some kind of a reaction happening inside the beaker. When it's exothermic, the energy is exiting to the surroundings. The surroundings will feel warm. But when I have an endothermic change and it's absorbing energy, it's taking that energy from the surroundings. So it's taking that energy from the surrounding air, from the surrounding container. So if the surroundings, whatever is holding this reaction, if they're losing energy, then the surroundings are going to feel cool to the touch. So like my beaker would feel cool to the touch. Any kind of an energy change is always the sign of a chemical reaction. It doesn't have to be that something is on fire. Sometimes it's that the container feels cold, and that's another sign that there was an energy change. It was that my reaction absorbed energy from the surrounding container. And so here's this use of our new equation, products minus reactants. And the idea here is that technically these values are heat of formation. So often they're negative or exothermic because energy is released when bonds form. And so we start with our products, and it's usually an exothermic value because that would just be naturally the particles that are being formed. This is heat of formation. So I can use those heat of formation numbers on the product side as is. But on the reactant side, it would be the opposite. That these values are for bonds forming, but on the reactant side, I need to break those bonds. And so that's why we have like minus the value of the heat of formation on my reactant side. It's almost like plus the opposite. So we mentioned in a previous unit that energy is required to break bonds. Energy is released when bonds form. It's the same amount of energy. The difference is just the direction of the energy flow. And so here these heat of formation values tend to be more legit for the products. The products are being formed. The reactants are not being formed. They're doing the opposite. I'm going to have to break apart the reactants. So you could also think of this as like delta H equals the total energy of my products being formed plus the opposite of the energy value for the reactants. The reactants are not being formed, we're breaking the bonds. And then overall, my energy change is just kind of a comparison of those two values.